Hello, everybody. This is Professor Ma, and this is the summaries on the sections of harmonic series in integral test. The name harmonic came from use in music. So these are the points which, if you play guitar, you know that these are the points you can touch. Then you touch lightly and pluck the string, then the string will wobble and they will vibrate uh, 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 in a wobbly fashion as shown over here. And if you touch a different point, like 1/5, 1/5, 1/6, 1/7, then you get produce a bunch of notes, harmonic notes, which are higher and higher. So pitch goes up. Hence the name for harmonic sequence or harmonic. If we add these numbers up, they call harmonic series. If you look at individually, 1/2, 1/3, 1/4, we get a name harmonic sequence. So we're going to look at the problems of a series, whether it's adding infinite many numbers, whether they converge or diverge. But before that, let's recall a fact from improper integral. That is the improper integral from 1 to infinity of 1 over x to the pth power. In particular, for p bigger than 1, say, for instance, p equal to 2, then we're talking about 1 over x squared. And if we look at this type of function, they are below 1 over x. And for p bigger than 1, then when I integrate it, then the integral is finite, okay? 0 to 1 to infinity, 1 over x squared, dx, you get a finite answer. Okay. But if you integrate p equal to 1, or in other words, if I'm integrating 1 over x dx, 1 to infinity, of course, I get log of x, and that, if I evaluate it, I get infinity. So 1 over x sort of x as a boundary, or the p function below it converges. Okay, it's below 1 over x. B-E-L-O-W, 1 over x. And all the functions above it, like p to the 1, like 1 over square root of x dx, then this will be infinite, because 1 over square root of x will be on top of 1 over x. Okay. So 1 over x serves as a boundary for the improper integral, whether they diverge or converge. And this turns out to be the same for the series, that is adding 1 over n to the power p, where n is an integer. Okay. And so let's go back to the problems that when we look at adding infinite many numbers and whether they converge, whether it adds up to be a finite sum or as an infinite sum. And we call that there are only two sums which we can actually sum the answers. One is the geometric, like this type, 1 plus 1/4 plus 1/8. And I know this one, they actually sum to 1. And then the other types are these, which we call, these are the geometric ones. And the other one we call this telescoping one. Telescoping, okay? And basically, these are tricky sums, which actually all the terms cancel. I mean, like what? Like sum of 1 over m minus 1 over m plus 1. Like for n's from, say, 1 to infinity. And then if you write this out, this actually is 1 minus a half plus a half minus a third. And plus, third minus a fourth. And you find out everything here really cancels. So this actually infinite sum actually adds up to be 1. In particular, this is 1/2. 1/2 minus 1/3 plus 1/6. 1/3 minus 1/4 is 1/12. And 1/4 minus 1/5 is plus 1/20. So this, in particular, this is the individual terms, and they sum to 1. Why these two examples? One more time, these are the only ones we can sum easily. Okay. Now, For the other infinite sums, the formula that's not as simple. For instance, instead of sum like this, and one or sum like that, or sum like for instance n squared plus 1, okay, or just n squared. The sum 1/4, 1/9, 1/16. What does this sum into? This is a difficult questions, okay? And actually, I'll leave that up here to check on Google what that's the answer sum into, and it's kind of a surprise, but it's not an easy process. But the key point is that the sum, infinite sum that we know how to sum, there are only two types. Then for all the other one, then the basic question is since we don't know how to add them to a particular answers, and the next question is whether they converge or diverge. Okay, so here's the first theorem that we observe about converging, that if we add infinitely many numbers, the sum is finite, then the terms of the sum must become smaller and smaller, become zero. So for instance, the case is 1 plus 1/2 plus 1/4 plus 1/8 plus so on. So this is equal to 1. And the terms themselves must go to 0. This is 1/2 to the n, it goes to 0 that I'm adding. Okay. And here's the proof. I'll let you browse through the proof. Basically, it goes to the definition of what we mean by a converging series. It's defined by its partial sum. Okay, and then the partial sum, you look at the difference of the partial sum, actually is the individual terms. This is actually the term an. But on the other hand, the partial sum, the limit goes to L, both of them, so its difference is 0. So therefore, the terms an must go to 0. But if we turn that situation around, suppose I know a bunch of, suppose I know the terms goes to 0. Does that mean that adding them will be a finite numbers? And the answer is, of course not. Okay. Oh, by the way, before I forgot, this is what you do to, these theorems tells you what do you do when the question asks you if a series converges or diverges. For example, I mean, sum twice of m plus 5 over 5m minus 3, okay? N is equal to 1 or infinity. And this asks you, does this sum equal to finite or it's infinity? Converges or diverges? Okay. So these are the kind of questions we'll be talking from here for next few sections. I mean, here is adding infinite many numbers, the sum finite or infinite. First things you check is if the term goes to 0. When n goes to infinity, this limit goes to 2/5. Okay, and this limit will go to 2/5. And in particular, what does that say? Meaning that if you were to write out what this series is, whatever term is, basically as n become very large, you adding a bunch of number that's very close to 2/5. If you're adding infinitely many number 2/5, you get infinity. Okay. First, make sure the limit has to go to 0. Okay, because if it's not 0, then you're done. It diverges. Okay, so this is the first thing you look at, and you can tell whether the series diverges or not. But if you turn the situation around, say, okay, now you check that the limit goes to 0. It doesn't guarantee the sum will converge. Okay, and here's an example where I have infinite many terms, and the terms themselves go to 0. Okay, but if I were to add them up, notice this particular sequence is produced in such a manner, the 2 1/2 and the 3 1/3 and the 4 1/4, each block adds out to be 1. And how many blocks? 1/5 and 1/6, even many blocks also, they add to be infinity, okay? Because each one of these blocks is 1. And so the infinite many blocks I can add up to be 1, so they add up to infinite. Okay, essentially this is the argument that we can pull for the harmonic sum. So here's a harmonic series. I'm going to add up all the harmonic sequence. Okay, 1 plus 1, 1/2 plus 1/3 plus 1/4 plus 1. I'm going to add 1/2 plus 1/3 plus up to 1/10. Okay, and I'm going to prove that adding this, keep doing this, I'm going to get to infinity. And here's how we're going to do it. 1/2 plus 1/3 plus up to 1/10. There are 9 numbers here, 9 numbers. Each one of those numbers is at least 1/10. 1/2 is more than 1/10, 1/3 is more than 1/10. So altogether they are bigger than 9/10. Next block, I'm going to add from 1/11 up to 100. There are 90 numbers here. Okay, think about it. The 90 numbers, 90 terms. And each of them is bigger than or equal to 100 because that's the last one. Okay, and so 90 times 100. So these blocks adds up to be more than 9/10 too. Now I do the next block from 1/101 to 1/1000. You can probably draw a conclusion. This is more than 9/10. And so I can keep taking these 9/10 of a block, and the blocks longer and longer, but they add up to be 9/10. And how many blocks are there? There's infinite many blocks. And so hence infinite many 9/10. Hence they add up to be infinity. Okay, so this is one way to prove that the harmonic series sum diverges. Okay, we do this block estimations, make sure each one is more than something. Okay, the diverging harmonic series and the remember the P functions. These basically are 2 sides of a coin, that in a sense, one's a continuous case, and this we call the discrete case. Okay, this usually referred as discrete, C-R-E-T, discrete, and usually we call this continuous case. Okay, and there's a relationship between these two, the adding the series and integrating the functions, and there's a relationship among them. Basically, if the integral is finite, converges, then the series converges. The additions versions. This is called the integral test. With one conditions, we have to have these functions. There's a decreasing function. So here's a statement of the theorem. Okay, so in particular, we're going to look at the P series. That is 1 over n to the P. So for instance, the P equal to 2, then I'll be looking at the sum of 1 over n squared. This, of course, is equal to 4 plus 1 plus 1/4 plus 1/9, and so on and so on. Okay, so these are called the P series, and they correspond to the peak functions from 1 to infinity. Okay, and we want to connect them. And here's a series. Here is the connection between the series and the function that defines them. Okay, so suppose I have a series, a bunch of a sequence defined by a function f of x. Okay. And if f of x is an eventually decreasing functions. Okay. So in other words, f of x can be doing something like that, but eventually it has to keep going downhill. But in the front, it can wobble. So this is y equal to f of x. And where is this f of n? F of n, of course, are the points where this n equal to 1 are points on 1, 2, 3, 4, 5, 6, and you add up the values, the y's of these points. Those, the blue points, you add up the y values. That's the series. That's this one. The integral, of course, underneath is this one. And the theorem says they are correlated. If one converges, then the other converges. And so it both converge or both diverge, provided, one more time, the functions eventually decreasing functions. Okay, and the proof's at the end of the PowerPoint. Okay. So the integral behaves the same as a series, provided, again, the function is decreasing eventually. And here's why it is so. I mean, for instance, I can have this sine square of pi x, right? And this for the integer values when I plug in n, and so n when x is equal to n times pi, so sine n pi 0. So this actually defines the sequence 0, 0, 0 for every n. So if I add them up, of course, this is 0, right? But on the other hand, if I look at the graph of this function, it's oscillating. I'm just picking up these 0 points, add them together. And so, but the integral, obviously, from 1 to infinity is divergence. Okay, and you know, this, the sum 0 plus 0, 0 is 0, converges, but the integral 1 to infinity of sine square of pi x dx of it, this is infinity. Now, what's wrong with this? One is converges adding sum, and one diverges or integrate. Well, it's oscillating. It's not. It doesn't fall down. That's why we need the function to be eventually decreasing. Then the two correlates, the sum and the integrals. Okay. So this gives us that the P series converges if P bigger than 1. It's exactly the same as a P functions. Okay. So just like the P functions, the P series, this converges, just like integral 1 over x to the 1.01 dx is finite. Okay, and just like integral integral of x to 0.99 dx, this is infinite from 1 to infinity. Okay. And we also have floor and ceiling theorems corresponding for sequences. We have floor and ceiling theorems for integrals, we call these. So for series, and so if I want to prove a series AN diverges, okay. So now here's the game. We will have, for homeworks, you will have a series, infinite sum. And the question will be whether the infinite sum converges or diverges. And the point over here is you have to come up with an argument that justify your claims. And of course, you have to make a claim first. That is, you want to say, oh, you look at the things, you say, oh, these diverge or these converge. If you want to show the problem diverge, one way to do it is compare to something that's to another series that's big. So I'm going to, if you can come up with a Bn and they show that Bn diverge, then you can you can conclude that your series An, since it's bigger, it has to diverge also. So this is the four theorems. So for example, does this diverge or converge? Okay, and notice this is bigger than 1 over n. Log of n is smaller than n, so the fraction is bigger than 1 over n. So adding log 1 over log n is bigger than adding 1 over n. But this is the harmonic series. 1 over n, the p series n is, n to the first power. That diverge. And the things I'm trying to add is bigger than that. So of course it diverges. Notice, make sure you have the logic correct, okay? That is, if you find something bigger than an diverge, it doesn't tell you anything about the sum of an. So think about that. And similarly, we have the ceiling theorems. Basically says, if you want to prove something converges, then you need to come out something that's bigger that converges. Since something is bigger converges, so you must be smaller, it has converged also. Okay, so for instance, does that converge or diverge? Well, let me compare with 2 over n squared. 2 over n squared, the denominator is smaller, right? So the fractions, so this fraction is bigger. In other words, I have 2 over n squared bigger than the things I try to add. But the sum of 2n squared, this is the p series, p equal to 2. Okay, p series. So we're going to keep using, we start comparing things to p series, and that I know converges. Okay, since that is bigger than my sum, so my sum must also converge. Okay. So, and these are the type of arguments that for the homework that you have to come up, okay? And in particular, if you want to make a particular conclusion, converge or diverge, you have to first say, I'm going to use what argument? I'm going to use the ceiling theorems, or I'm going to use the floor theorems, and then you have to produce specifically that comparison, the Bn, the sequence Bn, that to compare with your problem, list them and show that the conditions of the theorems is correct, that A is bigger than B or B is bigger than A. And then show the corresponding behavior, say, oh, B converges, therefore A converges, or B diverges, A diverges. And the logic has to go in the correct direction. Okay, so and make sure you do, and that's different from your usual exercise. So on a test you will have to come up with the specific theorems you're going to quote, the specific condition of the theorems it's met, and then you can quote the theorems to make the conclusion about your problem. Okay, and that's it. Until next time, bye bye. Okay.